Hello, everyone, and welcome to another wonderful day of chemistry. So, today we finally going to start talking about real chemical reactions. So far, most of what we've been focusing on is just how we can change the state of a system. So, changing the volume, pressure, and temperature of a system. But it turns out one of the things we often want to care about is how a chemical reaction occurs. And because, as we said at the beginning of the chapter, energy can tell me a lot about how the energy moves in and out of a system, but it can also very much tell me how favorable a reaction is. So we really want to care about how energy moves throughout a reaction. Typically, we're going to want to use enthalpy over internal energy, and you've kind of seen some of the reasons why. Because internal energy specifically looks at isochoric conditions. But oftentimes we don't do reactions under a constant volume. Instead, we do them in an open container under constant atmospheric pressure. So enthalpy often is a little bit more based in what we tend to look at on a daily basis. The other big thing is that we can go ahead and, since we're looking at enthalpy, and we're going to assume that the PV is going to be fairly low, we're going to be looking at how the energy of a reaction changes using that isobaric heat. Because again, that isobaric heat can be related to the change in enthalpy of a system, especially if we have minimal temperature change. Now, the big thing is, since we want the only thing we're really looking at is how the energy of the reaction changes to prevent any of the complications of PV work and as well as changes in internal energy from heating and cooling. We're going to try and keep standard pressure and temperature relatively constant. So we're usually going to be using constant atmospheric pressure, 1 bar, and room temperature at 298. So we're going to designate these as standard state conditions. We also want to keep N relatively constant, and we often do this by looking at molar properties in terms of the size extensive ones. And we can really express this by looking at standard state. And because what we really care about is change in energies, we're going to be looking at enthalpies of reaction, where you see this naught or this zero superscript representing our standard state conditions for a reaction. And we can designate the change in enthalpy for reaction as simply what's the energy of the products minus reactants, and we get a nice state function of change. So one of the simplest types of reactions we can deal with aren't technically chemical reactions. Instead, they're just simple phase changes. So for example, I can look at the vaporization reaction as liquid water becomes water vapor or steam. And we can figure out the enthalpy of this vaporization by simply taking the enthalpy of the gas minus the enthalpy of the liquid. We can do a very similar thing for other phase changes, like looking at the enthalpy of fusion, which is simply going from a solid to a liquid or melting. Now, one of the really useful things we can do is enthalpy as a state function. So as long as I know the initial state and the final state, it doesn't matter how I get there. So this means we can often add together reactions as long as we have the right initial and final state. So for example, I can go ahead and look at a sublimation reaction, which is water going from ice or solid to water vapor or gas. Now I can get this by going through that liquid intermediate. So the change in enthalpy of sublimation will be the same as adding together the enthalpy of vaporization plus the enthalpy of fusion. Now, this idea that I can add together enthalpy changes as long as I get the right initial and final state, so more or less the enthalpy behaves as a state function, is colloquially known as Hess's law. And it's one of the more powerful things in enthalpy. And we've seen this when looking at other, say, PV changes. It doesn't matter if I go through an unrealistic intermediate if I have the right initial and final state. Also, similarly, we find because of the nature of state functions, the enthalpy for one reaction has to be the exact inverse for the opposite reaction. So the enthalpy of going from liquid to gas, or sorry, from solid to liquid, or fusion has to be the exact same magnitude but opposite sign as going from liquid to solid, or enthalpy of freezing. Similarly, the enthalpy for vaporization and condensation have to be of equal magnitude but opposite signs. And this is a very useful thing. So again, if we're looking at the enthalpy of reaction for a more complicated case where we have multiple stoichiometry, so going from J to I, with various stoichiometric coefficients, we can do this by simply adding together the enthalpy of all the products, again, times their stoichiometric coefficients, minus the enthalpy of the reactants. And a good idea here is that multiplying the coefficient times the enthalpy is the same thing as just adding the enthalpy of the product I number of times. So this is actually fairly robust. But unfortunately, this just kind of keeps moving the uh, uh, our metric. Because remember, one of the reasons we care about enthalpies of reaction or changes is because they tend to be easier to observe, and enthalpy and absolute enthalpies, and just like absolute internal energies, are a little bit arbitrary in terms of point of reference. This means that we often have some issue picking a good reference enthalpy. Now, there's a couple of options, but the two most classic are going to be enthalpies of formation, which is going to be the amount of energy needed to generate 1 mole of product from the constituent elements in their most stable state. So, for example, if I'm looking at, say, glucose, I need to find the most stable form of carbon, which is just going to be graphite, hydrogen, which is going to be hydrogen gas, and oxygen, which is going to be oxygen gas. So again, this is where it's good to always keep in mind what the most stable form of any element is, because you're going to reference that in its most stable state. So always keep an eye whether you're talking about diatomic or monatomic species. And remember, we're not just talking about solid carbon, because there's many allotropes. It's specifically going to be the most stable form, or graphite. And as a result, we find the enthalpy of glucose to be negative 1,273 kilojoules for every mole I make. Because again, we're looking at 1 mole of the product. This is probably the most common form of reference enthalpy you'll find. However, you have to be cautious, especially if you're looking at a lot of chemical engineering textbooks. There's another common enthalpy you'll find, and that's enthalpy of combustion, which is often a little bit easier to measure. So enthalpy of combustion you'll get by taking your bomb calorimeter and combusting 1 mole of the relevant species with plenty of excess oxygen. And that means the products are going to be the relevant oxidized species. So carbon becomes CO2, hydrogen becomes water, as well as you have to watch out for the peskiness of other species such as nitrogen or the halides. Now, notice there's a slight difference here because formation, we're looking at the energies of a product. For enthalpies of combustion, you're looking at the enthalpies of a reactant. That means that if we try and do the simple products minus reactants, which are based on the stability of the product, we have to watch out for the fact that since we switch the side, that means that when you calculate the enthalpy of reaction based on combustion, you need to flip the sign as well to compensate. We're looking at reactants instead of products. If you don't do this, you'll have the right magnitude but opposite sign, and it's a common problem to watch out for. If you need to be really sure you use the right reference point, literally try and add together all of the relevant reactions, so all the relevant formation reactions or all of the relevant combustion, and make sure that everything cancels out appropriately. It's the surest way to make sure you haven't made a mistake. Now, one of the big things is once we have a enthalpy of reaction, you can often combine this with other reactions to make the reaction that we actually care about. So for example, let's say I go ahead and I look up the enthalpy of combustion of glucose. Well, the enthalpy of combustion usually references combusting our solid with oxygen gas, that should be fine, to make CO2 and gas and steam. The problem is if I'm going to do this reaction at room temperature, I don't make steam, I make liquid water. So I need to find a way to change this reaction to the reaction of interest. So what I can do is I can go ahead and take my enthalpy of combustion reaction. So if I want to find the steam instead of the liquid, I can take the combustion reaction, which references liquid water, and combine it with the vaporization reaction. And when I do this, add these two reactions together, we'll find that the liquid water terms cancel. And by adding these two terms together, we'll get the exact desired product. So by adding together the combustion and the vaporization, but notice I have 6 water molecules here, so I have to multiply the vaporization by 6 to cancel out all of them. This will get me the right reaction, and when we add these together, we find out the enthalpy to generate the steam is a lot less favorable than just to generate liquid water, because again, it will tend to want to condense. So again, this is a good reminder of you can always get the reaction you care about by adding together maybe known reactions that you can look up in a table, but also a good reminder, make sure when you're picking reactions that everybody is in the right phase. Otherwise, your energies can be off by a good fraction. So next time, we're going to look at how we can go ahead and correct these thermodynamic energies, which are all given at standard state, for a non-standard state. Specifically, what do they look like at different temperatures? Until then, take care.